this was sort of an elaborate aside. So here what I meant by writing theta was just a pure state with, let's say, the expectation value of the energy that agrees with the thermal expectation value of the energy at inverse temperature theta. So that's what theta means. Actually, it doesn't need to be like I said in Hamiltonian. The important thing is that it should have almost all states with the right expectation value of the energy will have this property. Yeah, this is I think, an underappreciated fact that in talking about thermal states and systems, you don't really have to drag around the thermal density matrix to talk about pure states. You just have to talk about relatively high energy pure states. Okay. Yeah, okay. So the squiggly is hiding a lot. So let's discuss that a little bit. Part of the motivation for this eigenstate generalization hypothesis comes from thinking about random states. So, for example, if we take a random state in a Hilbert space here, and then we look at a subsystem, then the density matrix on that subsystem will be the same as the maximum mixed density matrix, which would be, in this case, the partial trace, the thermal density matrix, up to exponentially small corrections in the degree to which the subsystem we're looking at is smaller than 2. So that's what this squiggly means in that case. But actually, for real systems, it's not as simple. Because for real systems, let's say we take an energy eigenstate here. The statistics of the energy here will not be exactly the same as in the thermal density matrix. In particular, in the thermal state, there's some slump in the distribution of energy. It's not a single energy. So what that means is that this squiggly here will have power law corrections in the size of A divided by the total system size. So in either case, if we're looking at small subsystems of a very large system, this will be very close to an equal sign. But whether it's exponentially close or power law close depends on, well, it's power law close for what I wrote here. Okay, so the point of this is that it's nice now to be able to think about the 2-point function and the inner product of two states, one where we act with phi at 0 on the thermal state, and one where we act with phi g on the thermal state. Okay, what we would like to see as a product of thermalization is that this quantity should go to 0 at large t. So let's just work out. Okay. So first of all, let's see what we get in a case where we have where phi is just a single harmonic oscillator. It's going to be a system that does not normalize. So for that system, let's say phi is equal to a d omega t plus a dagger. How is the writing class doing now, by the way? Is it okay? No. Could somebody tell me whether they can see what I'm writing? Yes, great. All right. Thank you. Okay. So this, we only care about the terms where we have 1a and 1a dagger. And if we write out 5t times phi 0, we get a term which is a dagger, d omega t, plus a dagger a. So we get two different exponentials, two different oscillating exponentials. This is the one that we would have got in the zero temperature state. This is the one we would have got in the zero temperature state. It's multiplied by the thermal expectation value of the number operator plus 1. So this one is multiplied by the thermal expectation value of the number operator. Okay. So what are these guys? So tell me what is the thermal expectation value of the number operator in the state at temperature, inverse temperature beta for an oscillator of frequency omega? Who remembers this? Does somebody remember how you're supposed to calculate it? Okay, well, I'm sure this is something we know, but the answer is n is minus omega. Like this. So we have these factors in here, we have these two oscillating exponentials. So this thing is not going to 0 at any time, and of course it shouldn't. What we have is a harmonic oscillator, and if we inject an extra quantum, it's going to sit there and oscillate. So what we'd like to do is to think about some interactions that can make this thing actually decay as a function of time. So what I think about in the case where we have a lambda phi to the fourth on field theory, so we have a lot of harmonic oscillators here coupled together by a phi to the fourth interaction. And then the thing that can happen if we act with phi to add a quantum to the system is it can become elongated with quantum we added, and it can collide with something, some other quantum, which is present in the thermal state, and we can have two different quanta come out. Okay? So this this is the cartoon to have in mind for what's going to be driving thermalization in this quickly interacting Silas force theory. We have a particle that we added, and if there were no interactions, then it would have just continued to oscillate. The 2-point function would not go to zero. But since we had interactions and there are extra quanta present in the thermal state, one of those can hit the quantum we're interested in, and it can get popped out of its state. So the right way to analyze that, the decay of this thing, that coupling the Silas force theory, is to consider a Reed-Thom propagator, where we take the propagator is equal to the fruit propagator. It's actually contained in the Truman self-energy. If we sum to something where we have this thing, which is the free answer plus self-energy. Okay? And as usual, the important part of this self-energy diagram for getting the decay of this correlation function will be the imaginary part of the self-energy. So, very roughly, we're going to get a propagator which looks like k0 squared minus k squared, and then we're going to be adding this self-energy. And the imaginary part of the self-energy is what shifts the pole in this propagator off the real axis and gives us the exponential decay. Actually, the right formula is that the 2-point function g of t will be like e to the minus gamma k t, where k is the momentum index for the particular oscillators that we're going to be correlating here.
So, just because those things like the interaction model will be a interaction I should go get it.
Here. Yeah, this is just this self-energy diagram. This is the self-energy. So this expression gives us the sum of all of these guys. This geometric series. No, so these are all true self-energies, and this equation will resum all of them. Yes. Yeah, so we can imagine, let's see, okay, so, yeah, let me not comment further on that. Okay, so the answer for the gamma is equal to the imaginary part of the self-energy k divided by the energy. And the actual correct way to calculate the self-energy is a little bit annoying. You have to do it by calculating the 2-point function on the Euclidean circle, which represents the finite temperature state, and then you have to understand the correct analytic situation. I'm not going to go into that in detail because the answer is just so plausible and really doesn't say how much to write. What we find for this sigma is that it's equal to the imaginary part of sigma. It's equal to, first of all, 2 powers of the coupling. The 2 powers of the coupling are because this diagram has one coupling here and one there, so it's proportional to lambda squared. And there's a factor, a thermal factor, which I always have trouble remembering exactly why we have this thermal factor, so let me ignore this. And then a closed interval. There's 2 loop momenta, and these 3 energies. I'm going to define this in a second. For those of you for which this is behind the plan, all I'm writing here is energy conserving delta function. And what this is here is an interval. And going beyond perturbation theory and studying this problem where we don't have a weak coupling is really impossible. People don't have a lot of techniques for doing this. But it's widely believed that this type of exponential decay of correlation functions is a rather universal feature of thermalizing quantum systems. There's another piece of evidence for this, which doesn't come from perturbation theory, which comes from numerical simulations of spin systems. So, for example, we can consider things simple spin systems, like this one, like a hybrid spin system. Where these matrices here are the Pauli X, Y, and Z operators acting in the different sides of the system. So this is an example of a nice chaotic spin chain, and enterprising people can take this type of thing and put it on a computer and exactly diagonalize this Hamiltonian, the matrix, and then construct the thermal state by taking the exponential of minus theta times the Hamiltonian, and then inserting these operators, one at time t and one at 0, and computing the answer, and plotting it as a function of time. And the equal you get in this type of system is something that looks like exponential growth or exponential decay for quite a while. You can't go through very long times because you can't study this in very large systems, because if we want to study n spins, then we have to use a Hilbert space that's a dimension 2 to the n. And the matrices that we'll be looking at, like Hamiltonian or the thermal density matrix, are 2 to the n by 2 to the n matrices. And your computer will just run out of memory. So people can study, it's a state-of-the-art dimensions, maybe 18 spins or something like that. So it's a very small system, but it's enough to see some of this very interesting dynamics. So these are things that one can do. One can study perturbation theory, you get slow but exponential decay, and you can study small systems, small spin systems exactly, and there you get exponential decay for a while. And this type of information has led to the following kind of picture for what happens to the two-point function. It should decay exponentially for a long time. I don't know what I'm drawing here. It's something exponential. And then at very late times, if the system has finite entropy, it should stop decaying and start oscillating. The reason it starts oscillating is because in a finite entropy system, the two-point function is a sum of oscillating exponentials. And that type of a function, a finite sum, or let's say absolutely convergent sum of oscillating exponentials, can't really go to 0 at big time. At big time, it can be small, but it has to be oscillating. The value that people throw around for this sort of oscillating floor is a value which is about e to the minus x. So we both scale up e to the minus x. And so the transition here happens at a time of about 10. If we assume that the two-point function is decaying exponentially for a time of order of entropy, it will get down to a size of e to the minus x, and after that point, we imagine that it oscillates above this floor value. Okay. Yeah, I wanted to present an argument for the e to the minus x, but maybe I'll do that if I have time. I don't have time at the end of the lecture today. Yeah, sorry, this is GMT. Which is actually, this is interesting. Since you asked, this is a case where it's slightly different to consider a pure state theta and a thermal ensemble. And the answer that one expects for a pure state is actually larger. It's e to the minus x over 2 with its final fluctuating floor value. Sorry? That's the value. Well, let's say the real part. We could draw for the absolute value, but then hit better number negative. Okay, so this has been a brief introduction to two-point functions. The thing I want you to remember is that we expect them to decay, expect them to decay exponentially. We can analyze it in perturbation theory and we get a very slow decay, but we can't analyze very well, even to calculate it conservatively is not one. Okay, the other aspect of thermalization that I'm going to discuss a little bit is this idea of a quench. So these two-point functions are diagnosing what happens if we take an equilibrium system and perturb it a little bit. And the quench is asking a very different question. It's asking what happens if we take some state and excite it all of a sudden to some very high energy, but very non-equilibrium state. So a model for this is a state Q, which is given by a product over X of some operators acting inside X on the deck. So if we have, let's say, a lattice version of the system, then we can act at every site in the system with some local operator OX. Because we're acting everywhere in the system, we're going to raise the energy by an amount that's extensive. We're going to turn this low energy vacuum state to some high energy thermal state. But it's going to be a very special kind of high energy state where all of the quanta are sort of uncorrelated with each other. You have created them all out of nothing, independently in each site in the system. And then what happens over time evolution is they interact and collide, and the correlations become more non-local. There are a few different types of quantities that one can imagine computing to diagnose the approach to equilibrium of this state Q. The next one is to consider the entropy of a subsystem A as a function of time. Okay. So at t equals 0, we just acted with these local operators. Actually, let's imagine local unitary operators on the vacuum state. So at t equals 0, the subsystem entropy will be the same as what we have in a vacuum. So, vacuum, who can give me an idea of what type of entropy you should expect to have for a subsystem in a vacuum state? So suppose we have some region, is there some geometrical feature of the region that would tell us what to expect for entropy in the vacuum state? Sorry? Yeah, the area. So we expect to have the entropy of the subsystem A at time 0 to be proportional to area of A. And this will be divided by community cutoff. Okay, and at a very late time, we expect that this thing will approach an equilibrium thermal state, and there what does one expect for the entropy? Yeah, you're expecting an extent of entropy, something proportional to the volume. Okay, and now instead of being a UV scale, this would be divided by powers of beta, the thermal scale. So in between, there's some interesting thing that will happen where the entropy grows from something proportional to the area to something proportional to the volume. And this is something that really cannot be computed. It actually hasn't even been computed how this happens in perturbation theory. The one case where it has been analyzed purely in field theory is the case of a single interval in a 1+1 dimensional field theory, where Calabrese and Cardi showed that this is completely determined by conformal invariance, and what happens is the entropy increases linearly from the area answer to the volume answer, and then it saturates. In general, though, this is much harder to calculate than these two-point functions, but the time dependence of this function for t less than 0, less than infinity, is an interesting probe of thermalization. How rapidly these correlations become non-local. Yeah? Could you say that again? How do we know that this function makes any sense? I mean, how do we define it? Yeah, so no, the entropy makes sense for any system, for any state. It's just minus the trace of the density matrix times the log of the density matrix. So SA of t means the following. We compute rho A of t, so that's equal to the trace over A complement of the state we have, which would be eta minus I ht, q, eta I ht. Okay. So this gives us the density matrix from subsystem A, and then we compute SA as a function of time, which is minus trace rho A log rho A. Yeah, so my entropy here, I mean the von Neumann entropy, which is defined for any state. Okay. Yes. Yeah, well, one expects it to be monotonic. Actually, one expects also that at early times they should grow linearly. Although, I'm not sure that one expected that before it had been calculated using black holes. So, sorry? Yeah, the type of function one expects for this is, one expects this. I better not draw this, I think. One expects something like this. That's the volume answer. Here I'm plotting f of t minus s of 0. So this is the type of curve one expects, and properties of this thing, like for example the initial slope, that will be interesting diagnostics of the thermalization property of the system. Yeah, in principle one would like to be able to calculate the slope, let's say, to a leading order in a coupling in a weakly coupled field theory, but I don't think anybody knows how to do that. It looks like a very difficult problem. Okay, so that's the introduction to thermalization without black holes. We discussed the two-point function, where we can use perturbation theory, or we can do exact diagonalization. We also discussed this other type of probe, the quench, where you shock the system out of some low-energy state, some locally correlated to high-energy state, and then watch it equilibrate. Actually, I should have mentioned that for this system, you can also do these numerics on spin systems. Again, for systems of opposite size, like 14 spins, one can plot this type of curve that looks a lot like that. Okay, yeah. Well, yeah, this is another thing that you can do to take all of a sudden a high energy state that's very, very far out of equilibrium. In that case, you might not have this feature that the entropy is small to begin with, so it depends on what the Hamiltonian was that you were using to begin with. Okay. So now, let me give a quick introduction to chaos. So first of all, we've been discussing so far relaxation to equilibrium. In the decay of two-point functions, saturation of these entropies, but in real-time dynamics, there are also features that are growing with time, exponentially growing with time. This is something that studying classical chaos is taught. So in 30 seconds, what I know about classical chaos can be summarized by thinking about this classic problem of a particle moving in a stadium that looks like this. This is a classical chaotic system. And what that means is that if we take a particle, let's say it's here, and it's going that way, and plot its trajectory, plot how some kind of a path, if we could displace the particle a little bit first, and then set it moving in it would have had a very different trajectory. And for the type of system, the displacement delta x of the particle's trajectory before and after we perturb it, as a function of time, will be growing exponentially in time, where the rate of exponential growth is called the Lyapunov exponent. So this is classical chaos. We would like to have some understanding of this in quantum mechanics.